Hello, welcome to the 8.2 day one. Today we're going to learn about the geometric setting. And in class what we did is I handed out dice to a few different people and I had them roll it. So we simulated 20 times rolling the dice and they kept on rolling until they got doubles. And I told them all to count how many times they rolled until they got doubles. And then we drew a histogram where uh, our y-axis was the frequency, our x-axis was the number of rolls until doubles. Some people got it on their first time. Some people, it took 21 times in order to get it. So there was a pretty big range in what people got, but it generally had an overall pattern that looked like this. So there were some in here. Some were a little higher. Actually, 21 was pretty far out there, but it looked pretty checkered here, like that. All right. Is this a binomial distribution? Most people in class said no, but they didn't know why. The reason why is there is not a fixed number of trials. So in a binomial situation, we would take 10 shots and see how many shots we made. And in a geometric situation, we would keep shooting until we made a shot. Alright, so this is the rules for geometric. We have to have a success and a failure, same as binomial. All observations are dependent, same as binomial. The probability of success called P is the same for observation, same as binomial. The only new thing, or different thing I should say, is the variable of interest is the number of trials required to obtain our first success. So that is how it differs from binomial setting. So if I want to find the probability of this dice deal, first we need to establish that the probability of rolling doubles is, there's 6 ways we can get doubles out of 36 possibilities, so that's 1/6. So the probability of getting that on your first try is 1/6. Probability of getting it on a second try is going to be 5/6, meaning you didn't get it on the first time, but we got it on the second time. So 5/6 times 1/6. Now, the third time we didn't get it, then we didn't get it, and then we got it. So 5/6 times 5/6 times 1/6. To get it on the fourth try, we didn't get it, then we didn't get it, then we didn't get it, but then we got it. So 5/6 times 5/6 times 5/6 times 1/6. So this next one, we could just say 5/6 to the fourth power times 1/6. The next one could be 5/6 to the fifth power times 1/6. And hopefully you're seeing this pattern. Now, how does this exponent relate to that number? So if we're looking for a rule, we can say it's 5/6 to the n minus 1 times 1/6. That's going to be the probability x equals n. Now, this is our general rule. Probability x equals n is 1 minus p to the n minus 1 times p. Alright, so for Korean shooting 75% free throw, what's the probability she makes her first one? That's 0.75. What's the probability she makes in the second try? Well, that's 0.25 times 0.75, which is 0.1875. Now, if a probability to get it on the third time is 0.25 times 0.25 times 0.75, which is 0.047, say. So the probability of getting on the seventh try is 0.25 to the n minus 1 times 0.75. Alright, now if we roll a die until a 1 or a 3 appears, that's 2 out of 6 options, so that's going to be 1/3 or 0.3 repeating is going to be my probability there. Now, can you take a second and fill in these probabilities? Alright, hopefully everybody's done. Now, we are going to fill these in. And our first probability is 0.3 repeating. Our next one's 0.2 repeating. Then is 0.15. Then 4 is 0.10, 0.07, then 0.04, then 0.03. And you can see this could keep on going and on forever until it gets to essentially 0. Now, the mean and standard deviation of a geometric random variable. If x is the geometric random variable with a probability of success p for each trial, the mean or expected value of a random variable is the expected number of trials, which is 1 over p equals mean. The variance is 1 minus p over p squared. So find the mean and standard deviation of rolling doubles with 2 dice. Well, the mean, you take 1 over the p, which is 1/6. We could do this on our calculator, or 1 divided by 1/6 is the same as 1 times 6 over 1, which is 6. Now, our standard deviation is going to be the square root of 1 minus p over p squared. So that's the square root of 5/6 over probability squared, which is 1/6 squared. So we can just take 5/6, divide that by 1/6 squared, and then take the square root of that to get our standard deviation of 5.477. Now we have a probability. The probability it takes more than a certain amount of trials to find a first success is 1 minus p to the n. Simple formula. It makes these problems really easy. What's the probability we'll roll more than 5 times to get doubles? So probability roll more than 5 times to get doubles. Well, using our formula back here, you take 1 minus p, which is going to be 1 minus 1/6, which is 5/6, to the 5th power. So the probability it takes more, the probability it takes more than 5 rolls is going to be 0.4019. And that's a nice, quick, easy way to get our answer. Now, a more complicated way, if you forget this rule, we can still get this by doing geometric CDF. So geometric CDF, if we hit second vars, it's geomet CDF. This means geometric cumulative distribution function. Now what we type in is our probability of success, which is 1/6. And then we do comma, and then we want to go up to 5. And that answer is going to be 0.598. So I'd want to take 1 minus 0.598, which is 0.402, which is what this would round to. So 2 different ways to get the same answer. This is a nice shortcut, but we could also get it using geometric CDF. What's the probability it will take Corinne more than 2 shots to make the first basket? The probability she'll use more than 2 shots is going to be chance of failure to the 2nd power. So 0.25 squared is 0.0625. Nice and easy. All right, and here is your homework for tonight. And this is the last day of the chapter, so good luck with this.